Yeah, you can go ahead.
Sure. Thank you for the introduction, Professor. Let me quickly share my screen. Yes. I hope my screen is visible to all of you.
Yeah.
Sure.
Thank you for the
Um,
introduction, Professor.
okay. So, hi, everyone, and thank you for being here today. I'm Yanamal Shivraman, currently in my final semester of Masters in Computer Science at the University of Utah. And in this seminar, I'll be talking about LLM agents and systems. Just a moment. Just a moment. Okay. So, systems that combine large language models with tools, memory, and decision making to act more like intelligent assistants or autonomous agents. So, we've all seen what models like GPT-4 can do. They're amazing at generating text. But when it comes to actually doing things like browsing the web or solving multi step problems or working towards a goal, these LLMs fall short because they cannot autonomously do something of their own. So that's where LLM agents come into picture. Today, we'll also explore what they are and how they work and exciting research currently shaping this particular field. And we'll also dive into 5 or 6 research papers that are pushing these boundaries. Um, yes. So before we move on to what LLM agents are, let's first understand why LLMs alone aren't enough. So LLMs like GPT-4 are amazing at, say, reasoning, writing, or even coding, but they're missing a few like essential elements needed for autonomy. First, they are stateless, which means each prompt is, handled independently. So they don't remember what happened in the previous interactions unless we manually feed that history into them. And second, they have no tool access. So if you ask an LLM to, you know, say what's today's weather or to look up something online, they cannot do it because it can only guess based on the training data. Third, LLMs don't have goals or planning capabilities. They can follow a single instruction, but they won't break down a task into specific steps, or they cannot track progress unless they are guided externally. And you have to have a check on them for LLMs to be able to plan or track progress or modularize tasks. And one more thing that we can talk about how LLMs fall short are how they are passive. So they only respond to what we give them. They don't proactively act or explore or improve their own behavior. So, of course, while they're powerful generators of knowledge, they lack the agency we associate the real world intelligence systems with. And that's the reason researchers are building something more, or something that uses LLM as a brain, something that harnesses the power of LLMs but adds tools to it, memories to it, and goal directed behavior. And that brings us to LLM agents. So now, having yes, Professor.
One second. Namha. So,
Yes, Professor.
I kind of like agree. Can you go back to the last slide, previous slide?
Sure, Professor.
So,
Yes.
uh, yeah, I agree. Point three, four, and five.
Mhm.
But right now, I think one or two, at least from ChatGPT, you can just keep asking, right? They keep a session, right? You can keep asking. They can enlarge the context, and also you can ask a ChatGPT the real time questions like what's the weather and what's the I don't know. I ask the questions like what's the current stage of
Mhm.
stock markets or something like that.
Okay. So, so at most cases, it's usually based on the historical data, Professor. And even with the current evolving, LLM machines, we have so the retrieval of data is completely based on historical data, and only in certain cases uh, uh, the machine reaches out to external APIs through external APIs and other browsers. But in most of the cases, the data is just unreliable, and it only depends on the timeline of the data that you feed into it. So basically, if the machine is just trained with data up to 2022 or 2023, it cannot go beyond that. So at most of the times, it's unreliable. It's okay if you're dealing with insensitive data like weather or any day-to-day activities, but when it comes to situations like biomedical field and everything, where the frequently evolving data or the rapidly changing data is essential, uh, these machines cannot handle like live data that is being updated very recently. So it becomes a problem when the research is dealing with sensitive areas like biomedical fields or financial fields where uh, data is evolving rapidly. Yes.
Yeah, thanks.
Sure, Professor.
Yeah, please go ahead.
Sure, Professor. So, yeah, having talked about the shortfalls of LLM agents, LLM machines, let's talk about what an LLM agent is. So, at its core, the LLM agent is just a system that wraps around a language model like GPT with the ability to think or plan or take actions in a loop with a feedback. So instead of just generating text and stopping there, the agent uses LLM to reason about what it should do next, and it takes that action, like probably calling a tool, and then observes the results and loops it again, all over again. So these agents typically include four key components. And at its core, we have the LLM, which is the brain, the power, which serves as the reasoning engine. And second, we have access to tools like calculator, Python interpreter, or web browser or API. So the agent can actually do things beyond just generating text. So the third is a memory, which helps it remember past steps, results, or important facts. And finally, a planning or a control loop. We have a planning or a control loop that keeps the agent focused on the task or a goal. So it just doesn't divert into other trivial stuff through across multiple stages. You can also think of this as moving a language model to a cognitive agent. So one that does not just respond, but actually acts. Now that we talked about what an LLM agent is, let's open up this whole black box of what this agent is and look at the anatomy of an LLM agent. So most LLM agents follow a loop, something like this, where the agent starts with a goal or a task, and then the LLM thinks or plans. It decides the next step using appropriate reasoning, and it executes an action, like calling a tool or searching a web or writing a code. And then the system receives feedback from the environment. This step is optional, like a response from an API or an error message. And the feedback can also be through human interaction. And this is stored in a memory, and the process repeats all over again. So this entire cycle of thought and action and observation loop allows the agent to, work through a big task step by step. And even if they're multi-step, long or complex, because we have segmented this whole phase into multiple modules and we have environment feedback in every loop, we can achieve the desired results of any task, irrespective of the complexity. And inside the architecture, so talking about the architecture of LLM agents, we have modules like a planner. Uh, so basically, we have three different modules that drive the architecture of an LLM agent. And the first one is a planner, which uses prompts to guide reasoning. And the second one is an executor, which can actually run commands or use tools, which actually gets into action. And a memory system, which helps the agent remember past context. And sometimes there's also a state tracker, which is like a monitor that ensures it doesn't repeat itself or lose track of the progress. So it's basically like a centralized authority or a monitor that keeps track of the whole system. And some example architectures for LLM agents can be the React that combines reasoning and action in a single loop. So basically, different architectures just explain how each of these different modules are placed and how they are combined or separated based on the requirement. And there's also AutoGPT that tries to be goal-driven and self-reflective without any external feedback. And there are also LangChain agents that are modular and good for chaining tools, like using different types of tools one after the other. So together, these components, they allow the agent to behave more like a real assistant or a problem solver, and not just a chatbot that you interact with and just get the knowledge out of it. So now that we've built a solid understanding of what LLM agents are and how they work under the hood, let's shift our focus to the research landscape, like a few insights into the current research landscape. So in the next section, I'll walk you through some of the most recent papers that are driving the space forward.
So the
And each
planner,
of these,
yeah,
yes,
I got a question. Sorry.
sure,
So
no
the
problem.
planner is the planner
Mhm.
so you put like LM prompting
Yes,
in the
Professor.
statistics, right?
Mhm.
So is this prompting the way the LM agent to implement the planner, or the prompting is just to activate the planner?
The LLM prompting is just to activate the planner because planner is itself by itself an LLM agent. So by itself is a different module that contributes to the LLM agent. So by LLM prompting, by from the user, the planner gets activated.
Oh, I see, I see, I see. Okay,
Yes,
okay.
Professor.
Yeah, that,
Yeah,
that makes sense. Okay,
sure.
okay. Yeah, go ahead.
Okay, Professor. Um, yes. So let's dive into some of the recent papers on this particular field. So the first one, let's talk about an agent laboratory. So it is using LLM agents as research assistants. And I know it's a big step towards completely starting to use LLM agents as research assistants, but let's look into what they're doing. Um, so it is basically a framework built to use LLM agents as research assistants. The key motivation here is the bottleneck that the researchers face currently. So the time, money, and limited bandwidth. And these bottleneck factors, they mean only a subset of good ideas get pursued because there can be a lot of good ideas that have the potential to be pursued. But because of these factors, the time, money, and limited bandwidth, most of them go unpursued. So this agent laboratory aims to flip this by offloading the execution of research ideas to LLMs. And the system operates through three phases. So the first one is the literature review, just like how every research is being conducted, a literature review, experimentation, and report writing. And each phase is handled by specialized agents, like a PhD agent for reading papers, an ML engineer agent for running experiments, and a professor agent for writing the paper. So, what's clever is that the system allows for human intervention. This system is not completely autonomous, and at every step, or they can involve human interaction, or they can also go completely autonomous based on how the user decides it should be. So here is a picture of how this whole methodology or this framework is being built. So talking about this, the the machine learning engineer solver tool is a standout. So it just doesn't generate code, but it also reflects on failures and optimizes the code iteratively. So it does not just generate the code and stops there. It takes in feedback and it optimizes the code iteratively using a reward model. So for paper writing, they use a paper solver agent, which constructs full scientific papers with specified format. And they also, reviews them using simulated reviewers. And they even refine based on the peer review feedback. So it's kind of surprising all of the research, the whole workflow of the research, and modularizing them into different agents and making each of these agents do a specific task. Um, in terms of results, the Owen preview model produced the most useful papers, and these are some of the results that the paper shows. And while the Owen Mini achieved the best experimental quality, and there is also co-pilot mode where humans guide each step. But the only problem with humans involving in each step is the cognitive overload. So once the humans get involved altogether, there's a lot of cognitive overload where users have to keep giving in feedback. So, and most importantly, the whole setup is super cost efficient. Like as we can see, it only costs about $2.33 per paper with this model. So the key takeaway of this paper is that It shows the LLM agents can meaningfully support and even partially automate scientific research workflows, especially if human collaboration is built in. But to this paper, there's a lot of drawbacks, other drawbacks as well, that I'll discuss towards the end of the spotlight section. Um,
Oh,
let's
is
move.
it system?
The first paper is done, Professor.
Yeah.
Yes. Mhm.
I'm curious.
Yes,
So
Professor.
agent laboratory is a system like you can install it in your your
Uh,
desktop, right?
no, it's not a system, Professor. So it's basically a framework, the idea that they've proposed,
Uh-huh.
and it's not a complete application. It's just a integration of different modules.
Okay.
So yeah, it's not a complete software yet.
Do they provide any website or any I don't know demo so that people can try with that?
Uh, right now, they don't have any demo with this, but I can look further into this paper for you and find the GitHub repositories and the demos that they have with this paper.
So do they share their GitHub repository for their
So there
framework?
are certain papers, certain other papers that share their complete GitHub repository for the framework, but for this particular framework, they don't have any explicit or public repository for
Really?
this framework.
Is this because they're running some business? This,
Oh,
yeah. Yeah, I'm really curious. Like if
mhm.
they can do this semi-automatically.
Yes.
It will be big speed up, right? If
Breakthrough. That's right,
research,
Professor.
they can
So
generate code.
yeah. So if they can just, if the researchers can just come up with a research question and just like prompt it, just like a prompt to this whole framework, this is going to, carry out the whole research forward. But the only drawback to this is that this framework cannot be creative as much as how humans are involved. So that's the only problem with this framework.
Yeah, but they can receive the feedback, right?
Yes,
And
they
keep
can just, yes,
you can keep updating it.
that's right.
So which venue is this paper published?
This paper was published in okay, just a moment, Professor.
It's a spotlight paper, right? I guess it's ACL
Yes.
or ICR. I don't know.
It's not ICEA, but I have the references to the papers. One second. I'll
What's the name of the paper?
it's Agent Laboratory using LLM agents as research assistants.
Yeah, probably I can search on Google.
Yes, Professor.
Agent laboratory. Oh, it's very new.
Yes, Professor. It's completely new. It was developed in 2025, the
Oh,
March of February 2025.
yeah, I suggest everyone to take a
Yes.
look at. Yeah, if this really work. Oh, they share their GitHub. They have their GitHub.
Okay.
Yeah, if it works, I don't know. Maybe all the researchers will lose their jobs.
No, Professor, that's highly impossible because these agents just keep working on stale data or historical data, but it's only when cognitive power is involved, the research ideas could be creative.
Okay. Yeah, but it looks like they only provide a website. There's no
Yes,
code.
Professor.
They just put
Yes.
the web page. There have some code. Okay. Experiment. Okay. Yeah, they got 4K stars. Okay. Yeah, very interesting.
Yes.
Um, yeah, so you've have you finished this paper? You want to proceed to next paper, or you're gonna continue discussing this paper?
I'm finished with this paper, Professor.
Okay, great, great.
Okay. Um, yeah, and now let's talk about another paper, which is like plan then execute. So it's basically a study of user trust and team performance when LLM agents are being used as daily assistants. So this paper basically tackles an important question. So how do people trust and collaborate with LLM agents when these agents assist in everyday tasks? So, the author basically builds a plan, then execute framework, and evaluated it in daily scenarios like booking flights or exchanging currencies. So, basically, in the setup, the agent first generates a plan, and it first generates a structured plan which users can review and modify. Then the agent then performs each step with the option for user to approve or override individual actions. So think of it like pairing with an AI assistant. You either let it go auto mode or micromanage it step by step. So basically, the authors ran a large scale user study with 248 participants across 6 daily tasks. So these tasks ranged between highly important and highly sensitive and low sensitive, ranging based on these. They also tested 4 combinations of user involvement: full auto and user involved planning, user involved execution, and both. So, so what they found out of this was the major question that this research paper deals with, that how the level of trust that users have with LLM agents. So if the level of trust is not that great, we cannot involve LLM agents into handling sensitive tasks every day. So throughout this experiment, they found out that the user involvement, generally led to better plans and more accurate task execution. But here's the twist. So just because a plan looked good didn't mean it was actually good. So because the machine generated a plan that is well formatted and looks attractive doesn't mean it was actually good or correct. And the users sometimes they over trusted the agents. So that's a key insight. The trust calibration is very hard. And also involving users at every step, led to cognitive failure. So while collaboration actually improves the performance, there's also a sweet spot that has to be found between full automation and human control to have that right balance. And this paper is valuable because it reminds us that building effective LLM agents, it is not just about the improving their capabilities, but it is also about designing human AI collaboration that just feels right, that just has the right balance. So it's all right, or it's amazing if we can build LLM agents with high capabilities, with its ability to reach out to other tools and perform experiments. But it is also essential that the users have that particular trust without like the problem specified here, the cognitive overload. Users are able to use that with trust in everyday tasks. So this is about the plan and then execute paper, and it's more
So,
of a
yeah,
literature
uh,
review. Yes,
yeah,
Professor.
question. So, uh, this paper is an empirical study about
Yes,
LLM agents, right? But
yes, Professor.
what specific LLM agents do they study on?
So they basically study on agents that deal with financial data that buys and sells stocks. Some LLM agents that are designed to book flights, or LLM agents that schedules meetings or something like general agents that plan everyday tasks, Professor.
Oh, so you mean they, where do they get those agents? Are those agents like open source agents?
Oh, they are open source agents, Professor. Yeah.
Oh,
Yeah.
okay.
They do not specifically build any particular agents for this. It's more of a study. So they employ existing available LLM agents, and they just perform this study, like to what extent users believe or trust these agents.
Okay, I mean,
Yeah.
so that means there has already been many LLM agents
Yes.
in the public domain. I mean, you
Yes,
can
Professor.
use them, but they just
Yeah.
okay, they just this paper just investigate
Yeah.
once. Okay.
It's more of so this paper is more of finding that thin line of how much human interaction is required, or human feedback is required to make LLM agents more reliable. Because like how the paper discusses, if there's too much human intervention involved, it becomes more like micromanaging, and there's a lot of the brain load is overwhelming for the users. And however, if we leave the complete process for LLM agents, like, and make them autonomous, there's they do generate plans that look fancy and attractive, but the problem is they are not feasible, or they're not reliable. So this paper just finds that right line between the amount of human interaction that's involved with LLM agents.
I see. I see. Yeah, interesting.
All right. Can I move to the next paper,
Yeah,
Professor?
yeah.
Yes. Okay. And moving on to the next paper, we have Auto Agent, and this is a fully automated and zero code framework for LLM agents. So basically, let's talk about this. When we talk about LLM agent development and all these fancy stuff, these most frameworks assume a developer in this, but in somewhere in this whole loop. So someone who's fluent with Python, LangChain, or prompt engineering. However, this framework is developed or designed for everyone else who are not completely into development. So the main question for this paper is that, can we create powerful and general purpose LLM agents with completely zero coding? And their answer to this is yes. So Auto Agent, this particular framework functions more like an operating system for agents. Users can describe what they want in plain English, like create a financial assistant that can analyze balance sheets, and the system builds the tools, agents, and workflows automatically. So basically, all of these LLM agents and the workflow that I've been talking about in the previous steps, they're created automatically just with plain English. And the architecture is pretty elegant. So we have an actionable engine, that the front end that the decides what to do, and modular agents that do the work, like browse the web, analyze files, or run code, and a self-managing file system that handles the memory. So there's also a component that uses self-play to iteratively improve how agents are built. So by this, we don't really have human intervention, but then this whole system has its own feedback. It runs on feedback by itself. Um, so so the results also back it up. The Auto Agent actually scored the second best on the generative AI agents benchmark, beating all other open source frameworks. And it also outperformed the LangChain and graph-based methods by a big margin. And most impressively, it also created multi-agent teams to solve math problems using majority voting strategies. And it does all of these things automatically. And this paper also shows what's possible when you lower the barrier to building intelligent systems, intelligent agents. And if it points towards where, so this particular system travels towards a goal where anyone, and not just developers, can actually build and orchestrate an agent system with, with nothing else, but no language or no tools or technologies, but just plain language. And we do have a code available for this, Professor. So this has been put up for demo for the public users.
Okay, so is this uh um I don't know, like they provide a framework, right? As the
Yes.
architect we show in a previous slide.
Mhm.
So do they do you need to train the whole agent framework from scratch, or is kind
Uh,
of like a plug in play, like you can inject
s- Yeah, so it's just so how it works is that it's just a generic LLM agent that has been trained with all uh, uh, basic data. It's a generic LLM agent, but when the user comes up with the prompting, like the particular instance or particular scenario that they want the LLM agents for, uh, this particular framework uses multiple features or practices to actually modify that LLM agent to narrow down or do to perform what the user actually wants. And it basically narrows down the workflow or the functionality of the LLM agents. So the users don't have to train it from scratch because this whole framework is aimed for people who are not into development or computer science. It's for general public.
Oh, so can I go back to the previous slide? I want to take a
Sure,
look
Professor.
architecture again.
Yes.
So I mean, they have already trained a
Mhm.
general
Yes.
agent, and
Yes,
then
Professor.
the task is actually specified by the prompt
The
from.
prompt, right?
Then they can do
Mhm.
anything you want.
That's right.
Oh, really? Isn't this like AGI?
Um,
So they have tested their agent in the like GAIA frame benchmark.
then that's right, Professor.
Okay.
Yeah, the generative AI agent benchmark.
Yeah, I'm a little bit skeptical. I mean, you mean they
Mhm.
really train just a general agent, which can, in other words, they can by
Mhm.
prompting, they can adapt to any task you want.
That's right, Professor. It's a long leap, Professor. So basically, when you have to adapt it to different scenarios, it's not just the tools that differ. It's also the kind of data that you work on, the kind of data that the LLM agents are have to work on or retrieve data to perform the task. It's a big leap for this paper, Professor.
Okay, so yeah, my
Mhm.
question is that when you want to this agent to adapt to your own task, do you need to
Mhm.
provide some data for that task so that the agent will be fine-tuned on that data set or not?
No, so you don't have to provide the data. You don't have to externally provide the data for it because it uh, uh, it it retrieves the data from. So in case you want financial, so just like how the paper explains, if you want the LLM agent to perform for as a financial agent and for financial purposes, if you give out that prompt, it's going to using retrieval mechanisms, it's automatically going to fetch the data instead of just you having to uh, uh, train it with a lots of domain specific data.
But will it? But
Mhm.
you still need to interact with that agent, right? And tell the agent that okay, it's not what I want. Is what is I want, and it keeps adjusting, right?
Uh, yes, Professor. It actually, yeah, that's one of the potential risk with this paper. But human intervention is actually required here for feedback is actually required for making it more narrowing it down towards the goal that we are trying to reach. But
Uh,
it's all going to be in plain English. We don't really have to train or upload
they
data
don't
or
need to update the model parameters
yes,
in any way,
yes,
right? Okay,
yes.
okay, yeah, okay.
Okay, Professor.
Yeah,
Can I move to the next paper, Professor?
yeah, certainly.
Yeah.
Yeah, I mean, the other
Mhm.
audience like Da, Keyan, Zhitong, Abhishek, Shaq, you guys can feel free to ask questions. I think these are very interesting line of research. We discussed about that before, right? So this is a hot topic. So look at the very first paper, uh, Gnap have introduced is published this year. It's just released on arXiv. So yeah, so we should certainly take a look at those works.
Yes.
Yeah.
Okay. Moving on to the next paper, it's basically a paper search algorithm or paper search framework, and it's an LLM agent for, as I said, comprehensive academic paper search. So one of the hardest things in research is if we can think of, is finding the right papers to begin with. And especially when the query is narrow and technical or multi-sided. So search engines like Google Scholar are great for broad topics, basically like you can just give in a research topic and then Google Scholar is going to give a lot of relevant research papers. But one drawback with that is that we need papers about, for example, if we need papers about, say, UCB-based algorithms for non-stationary reinforcement learning. So when we have queries that's something so particular, uh, Google Scholars, search engines like Google Scholars, they fall short. So this paper search algorithm tackles this by turning the whole search process into a coordinated agent, more like a workflow. So there are two agents in this particular system: the crawler, which actively explores citation networks and it searches for results, and the selector, which reads each paper and decides if it truly matches the user's input, and it narrows down all the papers that the crawler has come up with. So the training pipeline is also really interesting. Since it's hard to supervise this particular kind of behavior, the authors use a synthetic data set, autoscholar query, built from related work sections of top tier papers. They then trained this paper search algorithm using imitation learning and reinforcement learning with a special variant that can actually handle long sequences, and they can provide rewards. So the results are impressive. So on a benchmark of the real world academic queries, this LLM agent beat out Google Scholar and GPT-4 and even hybrid GPT plus search system. So um, yeah, so here's a methodology. And they've also found out more relevant papers and few irrelevant ones than all the baselines. So basically the result is not just 100%, it didn't just give 100% accurate results, but yeah, they give out a few irrelevant ones as well. But the percentage or the proportion of the more relevant papers are higher than all the baselines. So in certain way, this paper search algorithm is doing what a smart graduate student might do. Search widely for all the papers and follow citations and skim through them deeply and filter precisely. So it is a great example of LLM agents going beyond the surface level search and into actual research assistance. So just like how we saw the modularizing or completely automating the process of the whole research, this is just a part of it where we have a crawler that that collects all the relevant papers based on titles or certain keywords in the abstract, and there's a selector that actually narrows down relevant papers and gives us the list of papers. So this is all about the paper search algorithm.
So I got a question. So
Sure, Professor.
is that it was trained using imitation learning plus reinforcement learning?
Yes.
Which agent? You got two agents, right? One is crawler, one is
Selector.
yeah. So
Yes, Prof.
both agents are trained through imitation learning plus RL.
So imitation learning should be, I'm not 100% sure about which agents are being trained with which kind of learning, Professor. So it's just a combination of both of it for.
Okay. So can you go back to the previous slide?
Sure, Professor.
Okay, so crawler agent is like use search tools plus citation crawling. Okay. Selector agent. Okay. So it's like crawler is gonna fetch a collection of papers. Selector will select relevant ones from them, right?
That's right, Professor.
Okay.
So it's a combination of a reinforcement and imitation learning.
Okay.
Yeah.
And you got two data sets. So is this data sets are their training are from their training data?
Training data.
Okay, these are they're training data. Okay.
That's right.
I got one question. So is there only 50 expert level complex query? That's
Mhm.
that's tiny. Oh,
Um,
is that really 50?
50K, right? I
no,
mean,
it
it's
just says 50 expert label. So it's for the training purpose, and because it's going to be kind of impossible to uh, implement all complex academic queries for a narrow down research like this. They just implemented it with 50 complex queries.
oh. Oh, okay. So this auto scholar query are more like synthetic, right? Yeah, okay.
Yeah, it's
That's
it's
synthetic.
generated for training purpose. So with the
Okay.
real world data, it's just 50.
Okay, then you guys you kind of manually fabricate some scholar queries. Or
That's
you
right.
get okay. Yeah, interesting.
Okay. So this is the methodology that of this particular agent.
I see. So you got a crawler given the
Mhm.
user query. Oh, so the user the same user query is given to both crawler and selector agent.
Yeah, so that's basically for crawler, it's divides or segments a user query into keywords where it can search for papers.
Uh-huh.
And that user query is the selector uses that user query in a more refined fashion to select or drop the papers. So the input is so this second input is not exactly from the user, but we're just using it again to refine the search.
Okay. Okay. Yeah. Interesting.
Mm.
And yeah,
Mhm.
one last question is
Yes,
there
Professor.
an agent based on some like pre-trained LLM or they
Uh,
train everything from scratch?
no, they're training it from scratch, Professor. There are no pre-trained LLMs that they're adopting to uh, build this on.
Oh, really?
Yes, Professor.
Then their data set is pretty small.
No, that's the reason they're using the synthetic data. So it's going to be difficult with the real-time data. So that's the reason they built it.
If you can take a look at data sets, even for the
Mhm.
synthetic data they provide is pretty
Low for.
yeah, it's pretty low, right? Like 50 expert queries and 35K. I mean,
Mhm.
it's probably is okay, but it's really small as compared to typical LLM training.
Training.
Yeah,
I think those are only used for imitation learning.
those for imitation learning?
Yeah. So I think what they are doing is like, so they use those for imitation learning and then they run the actual algorithm. So it's infinite until the algorithm converge.
They run what algorithm?
The PPO, the actual R,
Okay, okay.
yeah. So that I think
Yeah, yeah. The question
R.
is that their LLM model, I mean that decoder only transformer. Um, I was just curious if that transformer is a pre-trained transformer, and then with some additional layers trained by RL, or is just to train everything, the whole transformer is trained from scratch. Yeah, that's my question.
Oh.
You're not sure.
Yeah, no, I'm not sure about that,
Yeah.
Professor.
Okay, that's fine.
Yeah.
That's fine. Yeah, because usually if you do this,
Mhm.
you're gonna start with some pre-trained LLM, and you probably will just add one or two layers, right? You just
Mhm.
fine tune that layer with say the reinforcement learning or imitation learning process.
Okay.
Yeah, but anyway, so it's
Yeah.
fine. Yeah.
Okay.
Yeah, you can go ahead. Go ahead.
Yeah, I'm not completely sure about
Yeah.
how they train the LLM agent, Professor.
Okay.
Okay. Now we this is kind of a specific case study, or uh, you know employing LLM agents for something that's more specific, domain specific. And so let's talk about drug discovery. So it's at high, it's a high stakes domain. And while LLMs hold promise, they're often blocked by two major issues. So first, they require heavy fine tuning for specialized tasks, and they also need new knowledge, like from ongoing experiments, something that's live or something that has just been produced, and the data that is kind of constantly emerging. So we call this paper CLAD, and this addresses the structure by the solution as multi-agent retrieval augmented system. So it doesn't just try to bake all the drug knowledge into a model, all the historical knowledge into a model. Instead, it treats the knowledge as a resource to be accessed live. So here is how it works. You have a planning team that decides which data to use, and a knowledge graph team that pulls in related drugs or proteins, and a molecule understanding team that combines domain annotations and combines or integrates external tools like external tools for this particular knowledge uh, for this particular domain. So there is also a prediction agent that puts it all together to answer questions like what is the liver toxicity of this particular molecule, and the system performs exceptionally well. So here's the methodology that I was talking about. So there are different modular teams for this particular drug discovery uh, domain, and they have planning team, knowledge graph team, or molecule understanding team, and a prediction agent. And this is how they actually handle different tasks.
So the
So
team
yes,
is a set of agents.
sorry, Professor.
Yeah, I just want to
Mhm.
the clarification. What does team mean? Does a team means
A team is an agent, just like how we had. While we're building that whole framework for the research, automating the research, how we had PhD agents, machine learning engineering agents, and different teams like that. So each team refers to different agents.
okay, but each team is only one agent or is more
It's
the more
it's just one agent, Professor.
Just
It's
one.
just one agent. Yeah.
Oh, I see. Okay.
Yeah. Yeah. So the system actually performs really well, and it also passed a lot of the industry benchmarks. There's also domain-specific models and GNNs on a wide range of tasks, and they also include uh, a zero-shot prediction and molecular captioning. And it even beat large models without any kind of fine-tuning required, because fine-tuning is kind of expensive. And even with fine-tuning, where you can go wrong is that domains like drug discovery are constantly evolving. And even with fine-tuning, you just adapt the system to the data that's already present. But this particular paper aims to actually retrieve it every now and then uh, uh, sequentially to keep it updated. So even without any fine tuning, this system actually surpassed all other huge models. So a big win here is the modularity and the interpretability. So each agent, they produce a human readable report and making it easy to audit or extend or optimize. So this particular framework, they show how LLM agents, when coordinated and augmented with real world knowledge, when they have access to real world knowledge, how they can power scientific applications. So all this while, one drawback that we were dealing with, that we were having in the back of our minds, were how LLM agents can actually deal with data that's been constantly evolving. So this particular paper overcomes that disadvantage, and it's actually augmented and integrated with real world knowledge.
Yeah. The
Yeah.
question is
Mhm.
they have quite a few different agents, right?
Yes,
So
Professor.
how do they get these agents? Is those agents are already existing,
They're
or
already existing, Professor. They're already existing that they just uh, uh, if you think about knowledge graph tree, it's an already existing agent that is just trained to perform that particular uh, um, functionality. Like, so knowledge graph team is the team that does not, actually go and deal with real-time data, but rather they deal with the historical data. Like, in terms of drug discovery, it comes up with knowledge that how two molecules interact with each other or what is the result of that. So it basically deals with historical data. So these are all pre-trained LLM agents that that are furnished or polished for certain functionality in each of these stages.
Okay, so they just they just developed the framework that how you can
Mhm.
well organize or
That's right.
interact with those existing agents.
Yes, Professor.
You can bring
Mhm.
different knowledge sources to
Yeah,
facilitate or accelerate your
that's
drug discovery process.
and because it's not one whole system of its own. Fine tuning is not required for a whole system, and so it's by that way it's very cost effective. It's not expensive, and it's only these certain small modules or agents that you have to uh, focus the functionality to a specific task. It's highly cost effective as well because you're surpassing or bypassing fine tuning the entire system for this particular field for drug discovery.
Okay.
Yes.
Yeah, but I'm assuming
Mhm.
that because you said that you need to get up to date
Mhm.
biomedical or biology knowledge, right?
Yes, Professor.
This one, how do you fulfill this? Is this planning
Mhm.
team will automatically um search
Um,
relevant data?
so yes, Professor, the planning team they search the relevant data, and this searching is not just from the older research papers or something. They also have access to external tools where they find out the recent findings in this particular research field. So there's also external APIs at work to retrieve the most recent data for the
Okay,
machine. Yeah.
okay, yeah, that
Okay.
sounds good. Okay.
Yes, Professor. So that's about the CLAD, the Retrieval Augmented LLM for drug discovery. And yes.
What is this paper published or also released very recently?
No, it's released very recently, Professor.
Okay, still
Yeah,
in
it's
alpha.
a
Oh
yes,
no.
Prof. Mhm.
Okay, yeah, yeah.
Yeah, it's a very recent paper.
Okay.
Um, let's move on to the last paper for the day.
Mhm.
And so it's the large language models as urban residents, and it is an LLM agent framework for personal mobility generation. So, what if we could simulate how people moved around cities, and not just with numbers and GPS points, but with actual language? So, that's exactly what this LLM mob aims to do. So, the author treats urban residents as LLM agents who generate daily activity trajectory using learned behavior patterns and motivation. So, basically, they're tracking how each user or the urban residents daily activities are for urban planning. So, here's a high level idea. The system basically has two phases. The first one is it analyzes historical trajectory data from each person. So where they go, when they go, and why exactly are they traveling? And this extract patterns using an LLM and some prompt engineering. So for each author, this pattern is being extracted. And then um, yeah, it retrieves the relevant past days, and they also, it comes up with a motivation and generates the next day's plan in JSON format. So this plan could include places, times, and reasons as to why they can move. So they also even provided two retrieval modes, evolving and learning based. So evolving is based on recent days, and learning based is using a contradictory or a similarity model. So what's very important is the interpretability. So every plan includes a reasoning string, like I want to visit a park this afternoon because I need fresh air. And that makes the agents more transparent than black box prediction methods. So it's not just you want to visit a park, but it's just that you also give it the reasoning as to why it has to generate the pattern. So yeah, so they evaluated this on a real world data from Tokyo, and their framework, the framework actually beat prior methods in replicating the spatial patterns and the temporal intervals and the semantic routines. So it also adapts to non very uncommon conditions like the pandemics. So the whole point of this paper is just to understand how the user movements when it comes to urban planning. So when you have to plan a city, and you have to understand where and when and why people move across different locations in a city, this comes in handy. So in a nutshell, this paper actually shows the LLM agents, they can actually simulate human behavior, not just logically, but also through language, linguistically. And that opens up like new possibilities in urban modeling or synthetic data generation and social simulation. So the whole point of this paper is just to, you know, um, um, show that these agents can actually simulate the human behavior as well. So
But do they train on any data, or is this, I mean,
no,
is
it's a pre-existing LLM agent that they train on, Professor. Yeah,
it,
that they fine tune. Yeah, so it's already available.
but how do they test? Because that means like you just give it a prompt and then it generates the, I don't know, the message,
Mhm.
the text that describes
Yeah.
the mobility of residents, right?
Yes. So they tested on a set of data. So all this while, all these people would have moved from one place to the other based on at a certain time or for certain reasoning. So they test these LLM agents against the previous data. So it's basically generating a trajectory for a particular person in say for example in an urban setting, say for example a city. So yeah.
But how do they generate? So you give what kind of
Mhm.
prompt are you gonna provide to let the LLM generate a trajectory?
Yeah. So we are talking something about so the one example prompt that I can give is that um, so basically there's a user that wants to go to the park who so they want to go to the park, that's the place, and in the afternoon because they need fresh air. So there is reasoning, there's timing, and there's also place that they want to go. So it's just a prompt that can include all these three data.
Okay. Then it can automatically generate the whole trajectory.
Trajectory, that's right, Professor. And
Um,
it also based on, because the user needs fresh air and everything, this LLM agent can also, like, the way it plans the urban model, it because the reason is to get fresh air. So
mhm.
based on how the other trajectories of other people are involved in that particular city, it plans accordingly.
Okay. Yeah, I was really
Yes.
surprised.
Yes.
Okay.
So it's basically more like Google Maps that uses GPS and everything, but it's more integrated with reasoning as well.
And is reasoning capability
Mhm.
also from the inside of the large language model. They don't provide any reinforcement learning to enhance
Uh,
ability.
no, Professor, they did not mention about any reinforcement learning. So it's again a generic LLM agent that performs this.
Okay. Which LLM did they use? Is
Um,
GPT-4 or is O1 or
the model that they use here is um, yeah, I'm not 100% sure about that, Professor. The model that they use, the agent that they use.
okay. Yeah, that's fine.
Yes.
Yeah.
Okay. Now, wrapping up the uh, research papers the research progress that we've been talking about in LLM agents. So we did see LLM agents do some impressive things, but there are also like major gaps between the prototypes and the practical and reliable systems. So all these LLM agents that we were talking about lay out a very plausible prototypes for LLM agents for different functionalities. But trust is one big issue. So in the plan and then execute paper, users often trusted or over trusted agents. So even when the plan was, slightly wrong. And at the same time, being too involved created too much cognitive overload. Another key issue is evaluation. So in Agent Laboratory and the paper search algorithm, the models actually looked good on paper, but human reviews told a different story. So we need better benchmarks that actually reflect the full loop of planning and acting and collaborating. So domain adaptation is also, very important. It's not non-trivial. It's non-trivial. So the CLAD or the drug discovery LLM agent shows that RAG helps in biomedical settings, but even then, grounding and ambiguity, they remain a problem. So especially when agents synthesize information across noisy sources. So one more thing is that scalability is also an unsolved challenge. So auto agent and the drug discovery, because they were just trained on very few data, they highlight the orchestration cost of multi-agent systems. So these auto agent in CLAD, they actually had multiple agents working together for that particular framework. And for the open world domains like urban mobility, how do we even ensure that they are grounded and they're semantically aligned and accurate? So these questions, they're not just technical, and they're actually human. And we are building systems that are meant to work with us and not just for us. So solving these will shape not only how we design the agents, but also how we live and coexist and work alongside them. Um, so to conclude, LLM agents, they actually represent a powerful shift in how we actually think about intelligence. They're not static prediction, but they're very dynamic, and they have to be dynamic and context aware, and the collaboration has to be context aware and mindful. So from scientific discovery to urban simulation, we've seen how agents can plan or act and reason across complex tasks. So this is just the beginning. And as we tackle the challenges of ranging from trust or grounding or evaluation or the scalability, so we are, not just building better agents, we're also defining the boundaries. We're redefining the boundaries of what intelligent systems can do and how they can actually work with us. So as we move or as we progress towards LLM agents, we're not just asking questions to the machine and getting trivial answers. It's also how we make them to work alongside us. So the whole future of LLM agents, they do not just lie in replacing the humans, but the main factor, the main point in lies in augmenting and optimizing what we can achieve together with LLM agents. And and that's how I would like to conclude my presentation.
Yeah,
So,
thanks, Ganappa. This is really, really nice presentation.
thank you.
Yeah, let
Thank
us
you,
know the
Professor.
picture and also the cutting edge research about AI agent.
Mhm.
It's very, very impressive. So any questions
Thank you.
from the audience, from other audience?
I have one for the multi-agent, like the drug discover. So if you use the multi-agent, and what's the difference between the data they used, like for the data for the drugs, and one is for the, I think it's like the drug, and the other is bio knowledge.
Hmm.
And then they just combine them, or the combine the result and retrain it.
Yes, that's right. So if I understood the question correctly, so we're talking about the importance of retrieving new data and combining it with the existing patterns. Is that, did I
Mhm.
understand it correctly? Yeah. So basically, when it comes to, dealing with molecules and drug discovery and everything, so there are two phases to it. So one is a prior knowledge or something that we just learn from the books, like how we, learn in biology classes back in school. There are certain patterns that doesn't change, like how two molecules interact with each other. So this knowledge is essential. And also the recent discoveries or, some changes or some kind of combinations uh, that produce certain results. So they are also combined with the patterns that are likely to be static. So it's more like combining both dynamic and static information together. Like static is what we read from the books and that is going to be unchanged. And dynamic is what the researchers or the scientists have found uh, recently over some certain period of time.
Okay, okay. Thank you.
Other question? Okay, yeah. Then we thank again. Wrap up. That's really nice.
Thank
Yeah. So we can discuss about
you.
next step. I mean, it depends on availability. But I do feel like those are very interesting. We have some data for AI agent as well, but it's probably not like uh, doing research or doing doing like flight ticket booking, those kind of stuff. But I guess we can leverage some kind of framework they propose here. I was yeah, I was a little bit surprised. Looks like most of those works they're not fine tuning or retraining
Yes.
anything, right? They're just based on existent
Mhm.
agent and then combine them and collect the user feedback. I don't know. They might have some like prompting method, right? So you can
Mhm.
type, the user can type some message and give the feedback, but I guess they will have some like processing step to convert it to be more effective prompt, right?
Yes, no, Professor. A couple of papers also deal with human interaction because so that's what they tested the papers with. So they tested few papers of them being a few agents of them being completely autonomous, and they have partial human interaction and a lot of human interaction in every different step. So the agents do take in the human feedback for refining their process. So that's what they compared against. And there's
Okay.
also retrieval techniques. So we did not talk about fine tuning techniques here, but we did talk about retrieval techniques where so in certain cases where they require where the timely data is essential. So we did employ so certain papers did employ retrieval techniques for their LLM agents.
Yeah, but once they retrieve the data, they're gonna
Mhm.
still I don't know, they're gonna put their data as the context, right, to generate the response. They
That's right.
Yeah, they don't, because they don't use those data to train to fine tune the
Mhm.
model, just to use
Mhm.
that as a larger context and
Yes, they just expand the context. They don't fine tune their
yeah,
model. Yeah.
okay, okay, yeah. Yeah, it is great. The question I was
Mhm.
all the comment I made it actually means that okay, the system probably, I'm not sure,
Mhm.
receive the user might type a bunch of stuff, right? But
Yes.
from our previous experience, it's better to insert some keywords or tags
Mhm.
and as a trick to more effective prompting. I'm not
Yes,
sure
true.
if those papers have mentioned those tricks, or they just didn't say anything.
Yeah, I think this one particular concept is being used in the paper search algorithm where the user's prompt is being, is converted into keywords in the
Yeah.
selector algorithm particularly. So for the crawler, I think the user's prompt is being taken as it is to collect a lot of papers across the networks. But with the selector algorithm, it divides the search into keywords. So, and that's how it will be able to select or drop relevant and irrelevant papers.
Okay. Yeah. Thanks.
Thank you.
Yeah, and thanks. And Zhitong probably, yeah, please update our group seminar website and Glampa.
Yeah, no, but yes,
yeah.
sure.
Can you please share with us your PDF version so we
Sure,
can
Professor.
put on our website?
All right.
Sure, Professor.
Okay, thank you. Yeah,
Thank you. Thank you all.
Yeah.